Everyone, welcome to the chemistry class. So last time we were talking about heating and cooling curves. If you have any questions related to that, please let me know in the comments. So let's do some exercise questions related to the topic, and then we can move on to the next one. All right. So these are very basic questions, and I was uploading the video last time, and I saw that on the YouTube there's an option for the quizzes. All right. So I was thinking about maybe I can next time when I upload the video, I can add like 2 to 5 past paper questions related to that topic, so that if somebody is watching it, they can give the quiz right there, and if they face any questions, they can ask me in the comment section. All right. So here we have a couple of questions. I'm going to go through this one by one and try to write their answers. Okay. So what is heating curve? I think its definition I have already mentioned. I'm going to keep it really brief here. Okay. So it's a graph. Okay. A graph or a curve showing how the temperature of any substance changes over time as that substance is heated, probably at a constant rate. Whenever you see the word rate, is probably related to some kind of change with respect to time. Okay, so that's it. Let's go to the question number 2. Explain how you can find the melting and the boiling point of a substance from the heating curve, like graph 1. Looking at the graph 2. So I drew a couple of graph. Okay. So if they give you a graph like this one, or maybe they would give you a graph like this one, how can you identify this is a heating curve and this is a cooling curve? If they give you one of these curves, how would you identify the melting and the boiling point? All right. The temperature stays steady at 0 degrees Celsius for over half a minute, even though the heating continues. So you are heating it, but the temperature remains constant. So the graph or the curve is flat there. Explain why using the term particles in your answer. So we have to explain it, and we must use the term particles in our explanation. So the melting point, I'm using the short form MPT. Melting point is the temperature at which, or you can say at the first flat or horizontal section of the heating curve. Okay, as you can see, right? And this is the point. It is the point, or you can say it is the temperature at which the solid would change to liquid. Solid changes to liquid, right? So it's very easy. Let me show you. Let's go back there and have a look at it. So this is the heating curve. We started at solid. This blue area I have highlighted at 0 degrees Celsius for ice. For different substances, for different solids, it would be different temperature. Okay, for ice it's 0. So this is the point where it gets flat. So this is the first flat area where the solid is melting. Okay, now using the same logic here, we can say the boiling point, let's call it BPT, boiling point, is the temperature at second flat area, or second flat, or you can say horizontal section, where the temperature doesn't change. Okay, the temperature does not change. This is the point, right, where the liquid changes to gas. Right? So that's the idea here. Let's go to the question number 3 there. Okay. So question number 3. So I think I read that before. So look at the graph. Okay, we saw the graph at 0 degrees Celsius for over half a minute, even though you are heating it. So let's try to explain that. Question number 3. So at 0 degrees Celsius, at 0 degree Celsius, the ice is melting. Okay, ice, which is basically solid, is melting, right? So at this point, even though we are heating it, the temperature is not changing. Okay, the heat energy at this point is being used to break attractive forces between the water molecules or whatever solid there is. Okay, forces between particles. In this case, these are water molecules, right? H2O molecules. So very easy. So even though we are heating it, the temperature is not changing, and almost all the heat energy is being used to break the attractive forces. We will discuss that, what kind of attractive forces are those in the future. So most of the energy is used to break the attractive forces between the water molecules, all right? So that the solid is being changed into liquid. Okay, so particles get that energy, particles gain energy, but what happens is that overall their temperature, overall temperature remains constant until all solid, in this case it's ice, has melted, changed into liquid. Okay, so this is what happens. Let's go to the next question. If you still have any confusion, please let me know. Which takes more energy, melting ice or boiling water? Oh, that's nice. So give evidence to support your answer. All right, let's talk about this. Question number 4. So before, like, you can pause the video and imagine, what do you think? Which would take more energy, right? So let's say, I told you the energy would translate into like energy, you can say kinetic energy, let's say. So kinetic energy translate into the movement of the molecule. Okay, so at the solid there's only vibrational movement. When you change to liquid, the particles are moving freely, but a little bit. But in the gas form, the particles are moving very rapidly, randomly. So there is more, like there's a huge change in the movement of particles from liquid to gas. Okay, there's less change in the movement from solid to liquid. So there would be more change in energy at the boiling point when the water or when the liquid is boiling. Okay, so boiling water, we can say boiling water or whatever liquid you are talking about takes more energy. Okay, changing from liquid to gas, right? So how would, like, they ask for evidence, all right? So you can see the horizontal section, right? The if you look at the heating curve, all right? So the horizontal section, if you look at your books, at the 100 degrees Celsius, which is the boiling point of water, that horizontal section is much more longer. It takes longer, or it takes more time, okay? Is much longer. It means it takes more time. More time means more energy, okay? So than in comparison to the flat section or the horizontal section at 0 degrees Celsius, which is basically the melting point of ice, right? So from there you can get an idea. Yeah, look at this. When I try to draw it, so you can see that this horizontal section I have drawn here, this one, I have drawn it a little bit shorter, okay? It takes less time. And this one I have drawn a little bit longer, it takes more time. So more time means you would have to heat it more for a longer period of time, so you have to provide more energy. So this is your evidence, okay? I hope you got it. Question number 5, looking at the cooling curve for water, about how long does the temperature stay at 100 degrees Celsius? So when I was drawing the curve, I was just, drawing it from a memory, okay, roughly, to just give you the idea. But if you look at your books, they would give you a very precise heating and cooling curve, okay? So you can look at those curves and give the answer, all right? So it would be about, I think so, 5 to 6 minutes, maybe 6.5 minutes, all right? That's the time it took. Okay, let's move on. That was 5A. Explain why the temperature stays steady for this time, even though you keep cooling the container. Okay, so it's almost the same reason in the reverse. Okay, same logic in the reverse. Right? So this was 5A. Let's talk about 5B. Why the temperature remains same, all right? So when steam or the vapors are being condensed, okay, vapors are condensing, when the steam is condensing to liquid form, which in this case is water, right? This is what happens at this point. At this point, the point they are talking about, okay? So in this case, in the vapor form, the particles are moving much rapidly. They have much higher energy, kinetic energy, and when they go into the liquid form, they release a lot of their extra energy, okay? So energy of particles is released. Released means overall it would decrease, and they move closer to each other. If they move closer to each other, right, so they would form more attractive force. or you can say stronger attractive forces of attraction. In this case, those would be hydrogen bonding uh, that exists between water molecule. Okay, so the kinetic energy at this point, when the steam or the vapors are changing into liquid, right? Although energy is released and particles are coming closer to each other, right? But what happens is that overall the temperature would not change unless and until all the vapors have changed into liquid, right? So you can say the temperature remains constant, kind of like constant, until all vapors have condensed, right? Until one state of like physical state have changed completely into another state, all right? Let's go to the next question. Hopefully that was okay. Look at the graph, or you can go to the book and see what is happening between point D and E, all right? So I do have a graph with me. Like if you look at the graph 4, okay, let me try to grab. Yeah, so basically I had to pause the video recording here, go back, get the screenshot of the graph, come back again. So I hope it will not cause any kind of trouble, right? Because I don't want to edit this. Okay, so this is basically question number, sorry, I have to, question number 6. Okay, let's go back. Question number 6. So if you go and look at the question, let me try to bring in this graph here. If you can look at the graph, it would make much more sense, right? Let's decrease. Okay, so this is the graph here, okay? So the question number 1, 6A basically, is that what is happening between points D and E, right? What's happening between point D and E? Let's color it. So D and E, this is a flat point and this is a flat point. Okay, I told you flat point are the points where the transition is happening, where one state is changing into another state. By looking at it, the temperature is going from, low temperature to high. So this is a heating curve and it's written right here, okay? If it was not written, you could still think that temperature is going from low to high. So it is heating curve. The horizontal point are where the transition state take place. The first horizontal point, the shorter one, less energy use, that's the solid melting. The next one is the liquid boiling. Okay, so this is the boiling temperature, close to here, like maybe like 2700, right? So let's talk about 6A. What's happening between D and E? How do I explain it? So at this point, this is about iron, right? So at this point, iron, let me check one more time. The question I forgot. What is happening between the points D and E? Okay? D and E. At this point, the iron is basically changing from liquid to vapors, right? Iron is changing from liquid to vapors, right? It's basically boiling, right? So you can keep that in mind, D and E. Now let's go and look at the next question, right? The next one is Look at this one. So between which point is iron turning into liquid? So basically turning into liquid means from solid to liquid, that's like melting. That's B and C, all right? So you can say between B and C, iron is melting. It means it's changing from solid to liquid. The last one question, 6C, would be give approximate melting and boiling point for the iron, right? So if you look at this, right? Look at this. So this is approximately like 1500, right? That's the melting point, okay? It might be slightly above 1500. So I believe, according to this graph, it would be almost 1500, okay? So melting point would be almost 1500 degrees Celsius. And the boiling point of iron would be almost, if you look at it, this is the boiling, okay? It's slightly above the midsection here, okay? So slightly above this midsection, okay? So you can say it's slightly above here, it's right about here. So that should be like 2750. It should be round about like 2800, looking at this graph, okay? 2800 almost, okay, degrees Celsius. Obviously I have not memorized their melting and boiling point. You don't have to memorize it as well. If they give you a graph like this, you can look at the graph, use a ruler, find out the exact value or closer to that, and give the approximate answer. All right, so that was all about the heating and cooling curves and the exercise. In the next one, we would go into the next topic, that is gas pressure. Okay, if you have any question, let me know. Take care.